Hello everyone. In this video, we are going to learn how to model an electrical substation using the SAFI TSE application. SAFI TSE is a leading structural engineering software for the analysis and design of various types of tower structures. The software accounts for the advanced structural analysis and design of steel lattice transmission towers, electrical substations, telecommunication lattice towers, guide masts, tubular poles, multi-pole frames according to the latest American and Canadian standards such as TIA 222H, TIA 222G, S37-18, ASCE 10-15, and ASCE 4811. In this example, we are going to learn how to use the advanced generation tools of SAFI to quickly create an electric substation composed of 2 columns and 1 beam. We will also generate the loads automatically according to a specific standard. We will add the transmission line loads to the structure. Finally, we will run the analysis and display the different graphical and numerical analysis results. In this example, we are going to use metric units. We will click on the unit system command to set the metric units as the default. We will then click OK to validate. The way the design parameters will be computed will depend on the selected standard. Thus, the first thing to do is to specify which standard you want to use. Click on the Codes and Standards button on the tower toolbar. In this dialog box, we select the ASCE 10 standard from the drop-down list. We then click OK to validate. The next button on the tower telecom toolbar is the Definition of Bolts button. The bolt dimensions and design properties are specified in this dialog box. SAFI TSE provides many libraries of standard bolts. For this example, we will select the 5/8 bolt from the ASTM A394 Type 0 library. We will then click OK to validate. The next step will be to define the connection schemas that will be used in this model. This command is used to define the layout of the bolts that will be used to connect the members of the structure, and it will be used to check the block shear, bearing, and tear-out failure of the bolted connections. This first connection schema will be assigned to all diagonals and redundant members in the model. We will assign the bolt and choose the direct, diagonals, and type of connection option. Then, we will define the dimensions of the layout by specifying the end distance, the bolt spacing distance, and the edge distance. Finally, we will rename the tab by double-clicking on the tab's name. The second connection schema will be assigned to the legs of the columns. We will click on the Add New Tab button. We select the type of connection to splice, single shear, for this connection schema. We then click OK to validate. The anchor rods are assigned to the column upon defining their location. Thus, the anchor rods must be defined prior to locating the column. Click on the next button of the Tower Telecom toolbar to define the anchor rod parameters. For each leg, we will define 4 anchor rod anchors with leveling nuts. We click on the arrow button next to the diameter field. We can then select from this list a diameter of the anchor rod with the associated thread pitch. We select a 1-inch diameter rod from the list, and we select ASTM A36 material from the material selector command. Rod yield and ultimate stress will be filled automatically. Finally, we will specify the concrete resistance and the leveling nut distance. Simply rename the anchor rod by double-clicking on the tab name. We then click OK to validate. Now, we are ready to start creating the tower. The first step will be to locate the tower. The first geometrical element that must be defined is the column. This column will then be used as a reference to create beams, diaphragms, and rigid connections. The column is located by its center line. The dimensions of the column are not defined in this step. It is only necessary to specify the position X, Y, and Z of the column on the ground and give it a name. The column is located at the origin, which is the default. Simply rename the column and then select the anchor rod in the anchor rods list. We create the second column by duplicating the first one and specifying a different position. The second column is like the first column, in this case, by defining the second column as slave to the first column, and in this case, the slave column will inherit the parameters of the master column. We then click OK to validate. Once the columns are located in the space, we can specify its dimensions. The column shape is determined using several trapezoidal segments which combined will form the column. In this example, each column can be represented by 3 segments. One for the base part of the column, another one for the attachment point with the beam, and finally, one for the peak. First, we will add a new tab and we will define the bottom width and the top width of the first segment. Segments in SAFI TSC are used in the model generation and may be used to calculate the solidity ratio for wind loads. We then create 2 other segments in a similar way. We generate the model again. We can see that the legs of the 2 columns are generated. The next step will be to assign sections to the legs of the tower. From the column segments definition dialog box, we can assign the main leg sections. First, we click on the standard section command to define the 3 angle sections of the legs. We select the material, we select the ASCE library, and the section type in this case is an angle section. Finally, we select the dimension from the drop-down list and click on the Add button. We add the other sections in a similar way. Then we click Close and then OK to validate. Now, after we finish creating the sections of the leg, we can assign the main leg sections for each segment. We can do it manually in each of the segment tabs, or we can edit the section column in the numerical table when we are done. Finally, we need to assign the splices to the legs of the columns. We click on the Connection button. For each segment, we select the splice connection schema from the list and we specify the number of bolts for the top and bottom connections. We then click on the OK button to validate and generate the model again. We can see graphically that all the legs have assigned sections. Before creating the panels, we will define the angle sections that we assign to the diagonals and horizontal members. Adding the standard sections to the database is a straightforward procedure. The faces of the columns are defined independently from the column itself. The faces are defined as a sequence of panels which will be assigned later to the column face. A given panel sequence can be assigned to any number of column faces. It is not necessary to create 2 identical sequences for 2 column faces. We are now ready to assign the panels to the faces of the tower. First, in the column face prototype dialog box, we will rename the current face tab to sides. Then, we will add the first panel by clicking on the Add Panel button at the top. We will then select panel type from the panel library and specify the height of the panel. A preview of the tower face with its panels is shown on the left side of the dialog box. We can increase the number of repetitions if we have similar panels. Next, we will click on the Section button to assign sections to the panel members. Because we already added the sections to the database, we will simply select the sections from the drop-down list. Then, we will define the connection parameters. We then select the connection schema from the drop-down list and we will specify the number of bolts. We then click OK to validate. We will continue adding the other panels in a similar way. Now, click on the Add Panel button. This time, the new panel will have the same parameters as the selected one on the list. In this case, we can just go and edit the sections for the second group of panels. We do not need to edit the connections because they have the same parameters. We can always and at any time edit the panels in a numerical table. After we are done assigning the panels to the side face, we will define a new face for the front faces of the tower in a similar way. We will then click OK to validate the new face data. The last step required to generate the panels is to assign the face to the tower faces. SAFI TSC allows the user to assign different faces to the tower. Usually this is the case for transmission towers and substations. We assign the face to the column face using the column faces identification command. Finally, we generate the model again. We can see that the two columns of the substation are generated including all the panels. In TSC Tower, the beams must always be attached to a column or another beam. They are not located in space as for columns. First, in the beam identification button on the tower toolbar, there are 7 types of beams: cantilever beams in the X and Z directions, beams between two columns, beams between a column and a beam, and beams between beams. Go ahead and rename the tab to Beam to clearly identify the beam. Then, select the column to column in the beam type list to create a beam between the two columns of the model. The elevation of the beam is measured from the origin of the global axes to the center line of the beam start. The elevation corresponds to the global y-coordinate of the center line of the beam. We will specify the elevation. Then, we will click OK when done. Once the beam is identified, we can specify its dimensions. The beam shape is determined using several trapezoidal segments which, combined, will form the beam. The same method is used for beams and columns. In this example, the beam can be represented by a single segment of constant dimensions. Click on the beam's segment definition button on the tower toolbar. Rename the tab Beam Segment. Then, set the dimensions of the segment. When a beam is defined with multiple segments, the length of each segment is of course important. However, if one segment is used to define the entire beam, and the beam is not a cantilever, the length of the segment may be set to any non-zero value. The segment will be stretched to the entire length of the beam. The beam layout allows you to specify how the dimensions of the segments will be used. For a beam of constant dimensions, either case will lead to the same result. We will assign the sections to the beam main members. Finally, we will click OK to validate. The faces of the beams are defined independently from the beam itself. The faces are defined as a sequence of panels which will be assigned later to a beam face. A given panel sequence can be assigned to any number of beam faces. It is not necessary to create two identical sequences for two beam faces. Click on the Beam Face Prototype button on the Tower toolbar to open the Beam Face Prototypes dialog box. The last step is to define the panels of the face of the beam. We will add the panels, associate the sections and connections in a similar manner as we did for the column face definition. Now that the face sequence for the beam is defined, we need to assign the faces of the beam. Click on the Beam Faces Identification button on the Tower toolbar to open the Beam Faces Identification dialog box. We will assign the face to 4 faces of the tower. We then click OK to validate. Now that the tower frame is completely defined, we can add the rigid connections and the diaphragms. Click on the Frame Prototypes button from the top tower toolbar to open the Frame Prototypes dialog box. Frame prototypes are used to define both rigid connections and diaphragms. We select a panel from the standard library, and we will assign the sections and connections to the members. The first frame prototype will be used for the rigid connection definition. We will rename the tab. We add a second frame prototype in a similar way. This frame will be used for the definition of the diaphragm assembly. We then click OK to validate. Now that the tower frame is completely defined, we can add the rigid connections and diaphragms. The rigid connections are used to enhance the bearing resistance of the column at the intersection of the beam with the columns to prevent the columns from collapsing. Click on the Beam Column Connections button on the tower toolbar to open the Beam Column Connections dialog box. First, we will create the rigid connection at the intersection of the beam with the first column. In the beam list, select the only beam of the model. In the beam column list, select the first column. Note that for larger, more complex substations, it is possible to define connections at the intersection of two beams. Next, we will assign the same frame from the drop-down list to the button and the top frame prototypes. When this is done, click on the button in the upper right of the dialog box to create a second connection which will be inserted at the intersection of the beam and the second column. We define this second connection in a similar way as the first connection. When the two connections are defined, click on the OK button. In general, for substations, the diaphragms are used to enhance the bearing resistance of the beams where the conductors are attached. Click on the Diaphragms button on the tower toolbar to open the Diaphragms dialog box. We select the beam from the drop-down list and we specify the position and the frame prototype. We repeat the same process for the second and the third diaphragm. When the diaphragms are defined, click on the OK button and save them to the database. At this stage, the model geometry is complete. We generate the final tower model by clicking on the button of the tower toolbar. Click Yes when prompted to confirm. It is now time to generate the loads and the load combinations. First, we display the General Loads toolbar. We use the wind and ice load generator to create automatically all the basic loads, and load combinations. The wind and ice loads generator command automatically creates the dead load, wind loads, wind on ice, service, ice load, thermal loads, load combinations according to the selected distribution method. We select the ASCE 74 standard as the distribution method. Then, we specify the terrain and wind ice parameters. Finally, we click on Generate. For the ASCE 74 distribution method, SAFI TSE does not generate the load combinations. Therefore, we must define them manually. We can add the transmission line loads on a substation as concentrated loads. On the General Load toolbar, we click on the Add Joint Load button. First, we select the two joints on the top of the column. Then, we click on the Basic Loads button to create a new basic load. Next, we select the basic load from the drop-down list and we specify the forces. Finally, we click on Add. Before running the analysis, we must define the load combinations. On the General Load toolbar, we click on the Load Combinations button. Load combinations are a combination of unfactored basic loads with load factors. A basic load with a load factor of 0 will be ignored for a given load combination. It is not part of this load combination. We add a new tab and we specify the load factors associated with each of the basic loads. Another way to generate load combinations is the Load Combination Wizard. The Load Combination Wizard assists the user in generating load combinations according to a specific code. The Load Combination Wizard can generate factored load combinations for resistance and stability, ultimate limit states design and verification, and for serviceability and fatigue, unfactored load combinations. After we finish adding load combinations, we click OK to validate. We can see on the screen all the generated loads on the tower. It is possible to display one or a selection of the basic loads by changing the display options of Loads and Load Visibility command on the camera toolbar. Another way to display the loads is the Numerical Tables. SAFI TSE provides detailed wind and ice table loads, including all the factors used to complete the wind pressure and ice thickness. To display wind loads on the tower in Numerical Tables, we will use the commands Member Wind Loads, Surface Wind Loads in the Generator Loads toolbar. In this case, the different numerical results can be filtered before being displayed. Depending on the requested type of results, the filters will be activated or deactivated, such as elements and basic loads. Ice loads on the tower are available as well in Numerical Tables. We use the commands Member Ice Loads in Generator Loads toolbar. We click on the Analysis button on the tower toolbar to analyze the model and check the design according to ASCE 10. Other types of analysis are available in SAFI TSE, such as p-delta analysis, nonlinear analysis, frequency analysis, buckling analysis, and seismic analysis. Click on Run. Graphical analysis and design results in SAFI can be displayed for all load combinations or a selection of them. We can select which load combination will be displayed from the Load Combination button on the Results toolbar. The dialog box can be left open while displaying the graphical results. We check the box in the Analysis section of the Results toolbar. We can see that the internal deformations of the tower are displayed. Different analysis results can be displayed graphically, such as deformation, internal forces, and reactions. Another interesting way to display results is through animation. Press the Animate button on the Static Analysis dialog box to start animation of the tower deformation. Analysis results can be displayed as well in Numerical Tables. The numerical results may be filtered before being displayed. It is possible to filter the displayed results to the selected elements or to display them for the entire model. It is also possible to display the results for a specific load combination. In addition, we can display results on individual members using the analysis elements results on the results toolbar. This command allows you to view the selected results at any calculation point in any element in the model. The window is made of a graph and a table. The Settings button allows you to change the graph title and the axes title as well as the title fonts. The two print buttons allow you to respectively print the numerical results table and the current graph. The Copy button allows you to copy the image of the graph to the clipboard to use for external applications. We deselect the Analysis Results checkbox in the Analysis section of the Results toolbar. Check the box on the Telecom Tower section of the Results toolbar. The design check results are presented in the form of colors corresponding to a percentage of design criteria. To display the results, select the type of results wanted in the upper section of the Tower Display Results option dialog box. It is possible to modify the display colors by double-clicking on the color rectangle to modify. The percentages of criteria associated to various colors can be also customized. It is also possible to view the numerical results for limit states for the entire structure or a part of the structure through tables. We click on this button in the Telecom section of the Results toolbar. Then, we select from the Display menu which type of limit state to view. We can select tension, compression, or connections. It is possible to check all the other limit states including the bending, shear and torsion, and combined stresses by activating this option in the Design Codes and Standards Parameters command. To display the tension compression diagrams for the legs of the tower, click on the Tension Compression Diagrams command in this list. This diagram shows the evolution of the axial forces in the legs, diagonals, and horizontal members according to elevation. It is also possible to display the diagram for a specific load combination and the envelope of the load combinations. Thank you for watching. Don't forget to subscribe to SAFI's YouTube channel and visit our website www.safi.com to stay updated on the latest features of the software.